Within ASAP, we can perform system analysis. What happens, what is the performance of the system as a whole, but we can also perform analysis on individual rays or sets of rays to determine all of the additive effects upon our optical system. And we'll take a look at an example. In this particular case, we have a Cook triplet design, and what we're going to do is look at the light from an on-axis point source, so collimated light coming into our system and then propagating through to an image plane. But in this case, instead of simply looking at the light from our infinite distance point source, which forms a distinct image at our detector, we're also going to take a look at some of the effects of the Fresnel reflections. We could similarly look at the effects of scattered light as well. Now let's take a look at our analysis. Now you might say that this is the on-axis performance and what we're seeing is the effects of spherical aberration, but notice the size of this detector. It's 42 millimeters on a side. This is the full size of the detector. Here is our on-axis image, and all of these other hits indicate other ray paths through our optical system other than our desired path. And what we might want to do is analyze or look at how does light, in this case, either make it to our detector or make it through our optical system as a whole. So let's take a look at everything that's happening in the system. And what I need to do first is consider everything, since we were previously just considering the detector. And now I'm going to issue a paths command. And what this will do is, because I've saved all of the data from this particular ray trace, ASAP can tell me about all of the paths that make it through this optical system simply by issuing a command paths. That went by rather quickly, so let's take this out of the docking view so we can see things more clearly. And there are 76 total paths that ASAP has encountered in the design. Many have a large number of rays and a significant percent of the base energy, and a lot of the paths have very little energy, first or second bounce Fresnel type reflections in particular in this case. We also see how much effort it took the rays to make it through the system. These rays went directly from the object to a particular surface. In this particular case, I know it's the image surface, without splitting or scattering at any surface. Some other of the rays split once, and others split twice. The double bounce ghosts are the most important in an imaging system, in that they have the potential of reaching our detector, which we saw in our prior analysis, but we also need to consider what's happening to any of the Fresnel reflections within the optical design. Now, in particular, I might not be interested right now in some of these very low energy paths. So let's say, for example, I only was interested in any ray path that had, say, more than 1% of the energy. I'm going to issue another paths command, but this time I'm going to put 0.99. What this says is any ray path that has more than 1 or more percent of the energy, tell me about. And let me hit the Enter key. And these are the ray paths. And most of the ray paths from ray path 1 up to ray path 12, with a couple of exceptions, in particular, for instance, ray path 5 is not there, has more than 1% of the energy. And we can see the number of rays, and we can see that they're all, in this particular case, either the direct path or single bounce or single Fresnel reflections. We can also look at each of these paths directly. And let me put this back into docking view so we can see our window here. And we do this by selecting the paths of interest and asking ASAP to give us the graphical information. And I have written previously a small macro that will do this. So let me come here and open up my file. And for lack of better, it's simply called Input 1. And here's what I need to do. I need to select a ray path. I'm going to do a vector rewind command to get rid of any currently stored data. I'm going to set my window, do a profiles overlay, indicate with the label what path we're looking at, and then plot the history of a particular set of rays. This file number right here indicates the save file extension I provided in my original file. But I have 12 paths I want to look at, and I don't want to have to run this macro 12 times. I use ASAP because I want ASAP to do the work. So what I want to do is put this in a loop. Easiest way for me to do that is to simply put my cursor in a blank line within my INR file, and I'm going to go to my templates directory, and my templates directory contains a series of basic information or templates on how to do particular items within ASAP. In particular, there's a do loop template. So I'm just going to insert the do loop template in my INR file at my cursor location. And this tells me how to set up a do loop in ASAP. Now, from my paths command, I know that I want to start at path number 1 and end at path number 12 and do every path. And this is what I want to do within that do loop, so I'm just going to copy this information and paste it. Let me just neaten this up a little bit. And then I want to comment out this information because we don't want to perform it again at the end of the do loop. The only difference is that I don't want to always print information about path 6. I want to use the wildcard to indicate exactly which step of my do loop I'm in, and within ASAP, that's simply the question mark. So each time ASAP goes through this, it will select the path identified within the do loop and then print that information on my profile. Careful now, don't end ASAP. We're going to work on currently saved data, so I just need to run this file. And there's my basic ray path, my imaging ray path, and now here are the other paths that had significant energy. And in terms of decreasing energy, it shouldn't be surprising to see that it goes in the order of Fresnel reflections off each surface, because obviously as we go from surface to surface, energy was lost on the previous surfaces by 2 Fresnel reflections, so as we go through, each subsequent set of rays will have slightly less energy. We're also going to get some second-order effects, some scattering effects. We could have scattering effects, although we didn't include that in this particular design. And when we're done, we'll take a look at a couple of files in particular, a couple of profiles in particular. Okay, so now we've gone through the process. And again, path number 1 was our direct image. And we got information about the energy in that path by looking at our history commands. Fresnel reflections off the first surface and the second surface, the third surface. What's interesting to note is that this energy is converging, but it's not forming a focus within our optical system. And from the fourth surface and the fifth surface, starting to get a little bit cluttered in there, but nothing to frighten us yet. But now let's take a look at this particular path. In this case, what we see is our Fresnel reflection off this surface is forming a significant image within the optical system. Now, if this is a photographic objective and I'm just taking pictures of the Tucson scenery, this probably isn't a problem. If this is being used in a high-powered laser design and I have concentrated energy in this region, it could pose a problem. This is, again, one of the reasons you'll need to do an analysis within ASAP. And again, that's the basic paths that we have available to us. And of course, once we see where possibly our internal reflections are and see if we have problems with those, the other thing we're concerned with is how did we get so much energy on our detector in the first place? So another piece of analysis we can do is let's consider the detector and all of the possible ways that energy made it to the detector. The first thing I need to do is select all of my rays back. Because of those previous path commands, we're not looking at everything. Now we are. Now let's just consider our detector. And now I'm going to issue another paths command. This paths command will only consider those ray paths that made it to the detector. And again, I'm going to undock my command output window so we can see what's happening. And we can see that 97% of the total energy in all of these paths makes it to the detector. We don't have all of the energy. The energy that went in the paths that did not make it to the detector is not included in this analysis. And what we see is we have a total of 18 paths, but of course once we get much below path number 10, there's very little energy left. And again, we can see that all of these are either the direct path or second Fresnel bounces. First Fresnel bounces, first order bounces, can't make it to our detector. So let's go back into the docking view. Let's run our macro one more time, but before we do that, let's make sure we consider all of our geometry again, instead of simply the detector. And I do that by issuing a consider all command. And now I'm going to put my cursor in my macro and run the file one more time. Now let's take a look at the results. Now, of course, path number 1 was our main energy path. Path number 2 is, in terms of energy concentration, a ghost path. Light comes in, double bounces off this surface before bouncing off this surface, again Fresnel reflections, and then forms an image at this location, so a rather concentrated distribution of energy at our image location. Path number 3, more spread out. Its image is located here, but let's zoom on in a little bit. Notice, again, we have a concentration of energy very close to this particular lens, just like we saw on one of the first order bounces previously. The next path, this lens is definitely seeing a lot of effects of Fresnel reflections. With a high power source in our system, this could cause a problem. Same with this path. Not much of a problem on the detector, but we do have an energy concentration that we might need to concern ourselves with. Again, the same energy concentration in the system, but a broad dispersed energy pattern at our detector. Very broad at our detector. Again, forms an image in this location, spreads out before it reaches the detector. And here's our last path that forms an image at this location. So again, depending upon our sources, depending upon how this system is being used, all of the ghost reflections may cause problems within our design. We also need to worry about the stray light we see at our detector location. Some of the other information we can get, let's again consider only our detector. And now I'm going to do the paths command. And in this particular case, we're looking at path number 1. And I can choose to look at the history of any or all of these rays. And let me just issue a history command. More information than we need, but we can select any particular ray and look at it. I could have also selected any one particular ray as well. And here's my data. Let's scroll this up a little bit. So what we see is the information about one particular ray. It starts at the object, and we see where it goes through the system. To object 1, to object 2, the front and back surface of the first lens, to the second lens, to the first surface of the third lens, where it then Fresnel reflects back to the second lens, where it Fresnel reflects back through the third lens, and then back to the object. And as the ray propagates, we can get its x and y coordinates, its z location, as well as the energy in the ray.